Hello, everybody. Happy British Science Week. And, and today is the 5th day of our live broadcast going through the different letters of STEAM. So science, technology, engineering, arts, maths and medicine. I'm Dr. Alice Mills, one of the co-founders and co-directors of Exeter Science Centre, working to create a STEAM Discovery Centre in Exeter. And today is M for Maths Day, so we are very happy to be joined by Dr. Gihan Marasingha, who is a senior lecturer at the University of Exeter in the Maths department. So, Gihan, thank you so much for being here. Remember, guys, if you want to comment or ask questions as we go along, please do put them in the comments. And yeah, so just if we can just start off, Gihan, and you can just tell us a bit about yourself and your path into maths. Why did you choose it?
Okay, yeah. So my start in maths, as with everyone, I guess, was primary school, doing maths in primary school, and I absolutely hated maths at primary school. I found it so tedious. I was wondering, why do I have to learn these times tables? It's so boring. So I hated maths at primary school. What I did like was science. I liked science and physics and that sort of thing, and computer programming. Once I got a computer. And the more I learned about physics and the more I learned about computer programming, the more I realized how important mathematics was to that. So I started reading these books in my local library. The ones I found most exciting were the Feynman Lectures on Physics by Richard Feynman. And then I read The Emperor's New Mind by Roger Penrose. And reading these books showed me that mathematics, the calculus, statistics, certainly for Feynman's book, were fundamental for doing physics. So I got into mathematics that way. And as I was learning to do computer graphics on my computer, making little computer games, I realized I had to understand trigonometry in order to make my little computer icons move around the screen. So drawing pictures as well. I guess there was an artistic aspect to that. I was using mathematics to draw little pictures, make little pictures on my computer. So it was, so I loved doing my little finger paintings and what have you. And I learned to do that on my computer via maths. But what really made me want to study maths rather than go into physics, I love physics. I had to, it was a tough decision choosing between maths and physics, was reading The Emperor's New Mind, because that book by Roger Penrose, it was actually about physics. It also went into some of the fundamental mathematics behind things. One of the fundamental mathematics ideas was that there are different kinds of infinity. There are different sizes of infinity. And I thought, wow, how can there be different sizes of infinity? So, or you might think, actually, it's quite natural. You might say, look at all of the whole numbers and look at all of the rational numbers, the fractions. There are clearly more fractions than there are whole numbers because each whole number is a fraction. Maybe 5 divided by 1 is a fraction. But actually, the weird thing is that you can put whole numbers in a one-to-one relationship with fractions. You can assign to each fraction a whole number and to each whole number a fraction, so that in that sense, there are exactly the same number of whole numbers as there are fractions. So from starting off thinking, actually, of course, there are different sizes of infinity, then you see, oh no, actually, maybe there aren't different sizes of infinity, because you can join up sets of seemingly different sizes. But then there was a proof by Georg Cantor, of the 19th century mathematician, who proved that if I take the whole numbers and I take all of the real numbers, so not just the fractions, but numbers that include things like pi or the square root of 2, if I look at that set of numbers, then there are more real numbers than there are whole numbers, that you can't find a one-to-one relationship between these two sets. And that was really mind-blowing, that you can prove that. I mean, it's not easy, but it's possible to find a relationship. But how can you prove that you can't find a relationship? And that kind of thing is you can only do in mathematics. Only in mathematics can you prove that something can't happen. So yeah, so that really excited me.
That's really cool.
How I got into maths. Yeah.
That's very cool. I've learned something there. Brilliant. So as Exeter Science Centre, as an organisation, we really want to highlight how maths is a thread that runs through the whole of STEAM. And I wonder if you can talk a bit about that, the importance of maths.
Yeah, absolutely. So I can maybe talk about that from the perspective of what we do at the University of Exeter. So we've got a number of different groups here at the University of Exeter looking at different areas of mathematics. So I'll talk in a bit about what I do myself, but before I come on to that, I'll talk about some of the applied mathematics areas. So one thing we've got is a big climate group. So as you know, the Met Office is located in Exeter, and we have these intimate links with the Met Office. We've got mathematicians who are trying to understand both weather and climate change, which is a very important thing, both on this planet and on other planets. How does climate work on other planets, like the bands of weather on Jupiter, sunspots, solar flares, all of that kind of thing? These could all be understood through mathematics, and that might be something you would have expected. But one thing that you might not have expected is that we can also understand medicine using mathematics, and illness. We can model, for example, epilepsy. So we've got researchers who are looking into epilepsy and are using mathematics to predict when seizures can occur in epileptic patients. So by doing that, we can actually save lives using mathematics.
Amazing. Yeah, that's brilliant. Yeah, so you just said just now you're going to tell us what maths you do. So yeah, I'd love to hear about that.
Yeah, okay. So my mathematical background is in an area called analytic number theory. So you might have heard of one of these big unsolved problems in this area, or you might not have, but one of these big unsolved problems in the area of analytic number theory is something called the Riemann hypothesis. I'm not going to say exactly what that is, because it's actually quite complicated to describe, but I can tell you some of the implications of the Riemann hypothesis. So this is something that was conjectured by Bernhard Riemann in the mid-19th century. So people haven't solved this for quite some time now. But what it's to do with is the distribution of prime numbers. So prime numbers are a bit like atoms for pure mathematicians. So they're the numbers out of which all other numbers are composed. And we've got a formula that tells us roughly how many prime numbers there are up to a given number x. So it's roughly x divided by the logarithm of x. So when I say roughly, there's an error term, and we've got an idea of what this error term is. But if we know the Riemann hypothesis to be true, then we can be much more precise about this error term. And there are other applications. So so that you might say, well, maybe I don't care about that. That seems all rather abstract. But there are actually practical applications of the Riemann hypothesis in the field of cryptography. That's a study of secret codes. So one thing that cryptographers really need to do is to be able to determine if a number is prime or not. It may not be clear to you why that is, but this is something that's important for cryptography. So in 1976, there was a mathematician called Gary Miller who developed a very fast test for primality, but we can only guarantee that his test actually works if we know the truth of this conjecture, the Riemann hypothesis that was conjectured by Bernhard Riemann in the 19th century. So if Riemann's conjecture is true, if Riemann's hypothesis is true, then Miller's test works. Otherwise, it doesn't.
Fantastic. That is crazy. I'm a physicist, and I find pure maths completely amazing. Like, just it's sort of in physics, I felt like maths was always my sort of tool, and the language of physics. But pure maths feels like something completely different and yeah, amazing. So yeah, thank you for that. So yeah, we are as an organisation really passionate about demonstrating the creativity of STEM, and so that's why we have this really strong desire to link up STEM and the arts. But you specialise in sort of creative teaching methods within maths. So can you expand on that a little bit for us?
Yeah, absolutely, Alice. So as you just said, I think when I started my route into mathematics, it was indeed through the sciences and using mathematics as a tool for doing science or engineering. But as I've learned more and more about pure mathematics, and now I'm a pure mathematician, I see that pure mathematics is actually something quite different. I would say that pure mathematics is itself an art, rather than it's just an art that has an application to sciences and engineering. So when you're writing a mathematical proof, there is a beauty to that thing. It is a work of art. It's like writing a poem or a piece of music or a novel. So what I've been doing with my mathematics students is trying to train them in the art of writing these beautiful mathematical proofs, and that's fortunately we can now go the other way and use technology to help us in creating these artistic things. So there's now a tool called Lean, which is an interactive theorem prover. So it's a computer tool that students can use to help them learn to write their own mathematical proofs. I've been working with students using that. So formal methods for mathematical proofs have had great success in a number of areas. So one area is the four-color theorem. So the four-color theorem is the idea, well, here's the question. Suppose you've got a map and you're coloring each of the countries a different color. So what's the minimum number of colors that you need to use to ensure that any two neighboring countries have a different color? That's the question. And the answer is 4, as you might guess. And so this was, only recently proved formally using a computer. So there's no sort of human written down proof of this, as it were, but a computer was used, or humans used a computer to help create a proof. Computers have also been used to prove something called Kepler's conjecture. So this is to do with sphere packing. So you've maybe gone to the supermarket and looked at oranges and seen how they're packed, and what's the most efficient way to pack oranges? Well, it's the kind of packing that you see in some crystals, and but can you prove that this is the most efficient way of packing oranges or crystals or what have you? And that's Kepler's conjecture. So that's something that has also been proved using these formal mathematical tools.
Yeah, very cool. Thank you. So,
Pleasure.
So yeah, we're trying to highlight just what an amazing area the Southwest is for STEAM research and industry. And yeah, have you got any comment on that? Why should we be proud to live in the Southwest from a maths perspective?
Oh yeah, absolutely. I mean, the Southwest is a great area to live in. So I've talked about our links with the Met Office here in Exeter. There's also a lot of research on the environment of mathematics that's going down in Cornwall, for example, in our Penryn campus, where we're looking at how mathematics can help understand alternative energy sources. So how we can look into wave energy, geothermal energy. So and this all links into mathematics.
Yeah, fantastic. Brilliant. We had an interview with Adam Feltman from the engineering department in Penryn the other day, and yeah, he was talking about how incredible the renewable engineering research is in this area. So yeah, fantastic. We have had a question. You did discuss it at the beginning, but how can there be different sizes of infinity? And that's from Emily Warman. So
yes. So yeah, it's quite interesting. So so I mentioned the way in which the two different sizes of infinity can be the same, that there can be a one-to-one mapping between two different sizes of infinity. So to prove that the number of real numbers is greater than the number of whole numbers, you use something called proof by contradiction. And Georg Cantor came up with a so-called diagonal method to prove that there are more real numbers than there are whole numbers. So what you do is you imagine that you could list all of the real numbers as a list, as maybe a list of decimal numbers. And what you can then do is you can, by contradiction, prove that there is a number that isn't on your list. So you've assumed you can list all the whole real numbers, which is essentially getting a one-to-one relationship between the real numbers and the whole numbers, and will prove that there is a number not on the list. How do you do that? Well, what you do is I can certainly find a number where the first digit differs from the first number on your list in the first place by just choosing, for example, if the first number is 0.1 something, I choose 0.2 something. And then I'm going to create the second digit to be different from the second digit of the second number in the list. So if the second number is 0.34, I'll choose 0 point something 5, for example, for the second digit. And I keep going down that list, and I will eventually have constructed a number that isn't on the list. But that contradicts the idea that I've listed all the numbers. So that proves by Georg's diagonal method that there's a number not on the list. And how can that be? Well, it can't be, because that's a contradiction. So we proved that there are more real numbers than there are whole numbers.
Cool, thank you.
My pleasure.
Awesome. So Gihan in the past has been known to set some very tricky logic puzzles on Radio 4. And he has offered to do one for us today. So he's going to set a logic puzzle now. And if any of you want to have a crack at answering it in the comments, please do. And we'll give you the weekend to mull it over, and then we'll announce the answer to it next week. So yeah, Gihan, if you wouldn't mind.
Yeah, sure. So this logic puzzle is an old school puzzle about 3 passengers, Amy, Bob, and Carol, and they're in an old school steam train. So they're going in their steam train through a tunnel, and because the engine isn't that efficient or something, there's a lot of soot that's being produced by the engine. And when they come out of their tunnel, their faces are covered in soot, but none of them has realized that their own face is covered in soot. They just see the other passengers, the other 2 passengers, and they all start laughing because they're so mean. They all start going, ha ha ha, your faces are covered in soot. But then Amy, who is well versed in logic, suddenly stops laughing because she has realized that her face was covered in soot. How did she make that deduction? That's the puzzle.
Okay. Well, thank you for that. Everyone get thinking. Get commenting. Have you anything else you want to add, Gihan, before we close for the day?
I just want to say, how awesome the Science Centre is. I'm very excited by everything that's going on there, and how awesome maths is, and STEAM. Actually, this is a new acronym for me. I'm liking it. So the A's for arts, right?
Yeah. STEAM has started to be used recently. So first they added the M for maths. For medicine, the extra M. Sorry, and then because traditionally it was just STEM, but yeah. They've now added the M for medicine, and also quite commonly now A for arts is being added, which we're really glad about, because we just don't want people to feel that they are either an artistic person or a scientific person, and that those things are separate, because they're really not. And I think you've demonstrated that beautifully by talking about the creativity and the beauty of pure mathematics. So thank you so much for that, and it's been really lovely seeing you, and thank you to everybody who's watched. Thank you.
Thank you, Alice.
Happy Friday, everybody, and see you again soon. Thank you. Bye.
Bye.